today's session chairman, Mr. Sushil Sharma. He is a chemical engineer. Currently, he is active in the IF. He is the honorary secretary of the National Council. He has developed color-changing coatings and foundry chemicals for Indian foundries and overseas market. Has presented technical papers in national and international levels. So I welcome Mr. Sushil Sharma and request him to start this session.
Good morning, everybody. Thank you, Sureshji. Well, today's first paper is presented by Mr. Anil Patel, who is Plant Manager, Vehicle Assembly and Engine Plant, Ford India Private Limited, Sanand, Gujarat. I welcome you, Mr. Anil Patel. His topic is Future Trends of Castings and Area of Opportunities. I will just brief you about himself. He is an electrical engineer from MS University, Baroda. He is a consumer-driven Six Sigma Belt certified professional by Ford Motor Company. Has experience in setting up and operating greenfield plants. Has worked in Ford plants in UK, Australia, China and Thailand on various production activities. Has received many global diversities and inclusion awards. I welcome you, Mr. Patel, and you can start your presentation. The presentation time is 20 minutes and then we will be having a question-answer session from the audience. Thank you. We are starting with the next speaker, Mr. Deepak Anaghan, who is engineer in R&D department of Metso India, Vadodara. His topic is environmental effect of foundry operations and technological solutions. May I request Mr. Deepak to start his presentation? Yeah. Thank you.
Hello and good morning, everybody. First of all, I would like to thank you, Indian Foundry Congress, for providing us the opportunity for the presentation into this stage. Our today's topic is environmental impact of foundry operations and the technological solution for its mitigation. Let me start with our company introductions. We are from Metso Autotech, which is a Finland-based multinational company having two foundries in India. One is in Ahmedabad, which is in operation since last 25 years. While second one is in Vadodara, which is in operation since last 2 years, which was totally greenfield projects. Vadodara foundry having a capacity of 2,000 metric ton manganese steel casting per month. While in our Ahmedabad, Metso Autotech foundry mainly produce pump casting as well as the metallic mill liner. And apart from this, few percentage of the casting they making for the manganese steel. So this is a bird eye view of our Vadodara foundry. So let me introduce myself. Myself Deepak Anaghan. I am working as a R&D engineer in our Vadodara units. So this presentation will be presented by myself along with the Darshan Vyas. So first half I will present and then Darshan will continue. So let's start with the introduction. We all are aware that the foundry industry is having many processing from starting of the pattern making to casting dispatch, and that all the processes involve some kind of the processes and that impact environment. For example, melting furnace fumes, grinding dust, as well as when we dump that use sand, that create the pollution into the environments. The Paris Agreement was held few years ago, and during that, all of the members are committed to reduce their carbon output as soon as possible. Apart from that, they also committed to keep global warming well below 2%. So to achieve this target, what foundry industry can do is they can use latest technological solution available in the market. So let's start with the what are the processes which causes the detrimental impact on the environment. So One of the process is molding and core making. If we see in the green sand molding, there are a lot of dust as generated. And in case of the resin bonded processes, variety of resin and catalyst use. And when we dump that sand, that is harmful for our motherland. So it's create soil pollutions. After the molding process, if we talk about the melting process, and we all are aware that this process is very energy extensive process, and lots of energy are required during this process to melt the raw materials and scrap. And during the melting process itself, huge amount of fumes are generated. In addition to that, before the melting, when we do the scrap cutting by any thermal means, that also creates the very tremendous amount of the fumes, and that need to be captured by any means to avoid its contamination to the environment. If we move forward, knockout and shakeout processes also create lots of dust in the foundry, and we are all aware about that the environment at the area of the knockout and shakeout area. That generate very intensive noise, and same has been with the machine where the mechanical vibration is used, which creates also noise pollutions. Apart from this both process, the fettling and finishing process also create or generate few amounts of dust. So here we have summarized the type of the pollutions and the what processes are involved to impact to the pollutions. First is the dust, as I already discussed earlier, that it is created due to melting, knockout processes, shakeout processes. Apart from that, that movement of scrap, furnace chargings, and shakeout, all these processes generate the dust. Also, the pneumatic transfer of the sand, that also create the dust. If we talk about the fumes, obviously the scrap cutting activity as well as the melting activity also generate fumes. Apart from that, when we transfer the mold and when we pour the casting, at that time the fumes are also created. The third one is the odor. It is generated in the casting and the mold cooling, as well as during the sand mixings also it is generated. During the melting activity and spraying and the coating activity, the odor is generated. The next one is noise. The noise is generated, as we discussed, during the knockout and shakeout machine operations. Apart from that, we know that the high frequency induction furnace also creates some noises, and short blasting booths and overhead cranes are a few of the sources of the noise pollution. The fifth one is the water, that water from the cooling towers, as well as where the foundry treatment process is water quenching, and that water is also creating the pollutions. Here, right hand side, the pictures is like fumes generated during the scrap cutting processes in the foundry. So this was overall the process that involves and that creates the trouble for the environment. I would like to draw your attention toward the latest technology that can help us to minimize its impact. The first is in the molding area. When we use the sand, the first of all is recycling and reuse of the molding sand. In today's modern foundry is tremendous pressure, not only for the reducing cost, but the laws related to environment getting very stricter, and that trigger for the foundry to invest for the reclamation of the sand. Nowadays, most of the foundry is having the mechanical reclamation, but now foundry can use the thermal reclamation unit to reuse maximum amount of the sand into that foundry, so they can minimize the use of the natural resources and they can reuse it very well. In thermal reclamation process of the sand, most of all the binder and all the organic materials are removed by the oxidation process in the chamber. First, the sand coming from the mechanical reclamation plant will passes through the cleaning tower, and at that time most of the metallic particles are removed before it's entered to the thermal reclamation unit. So the thermal reclamation system itself fluidized bed design with a gas and mixture, providing the fluidized medium and ignite on the sand bed via gas nozzle. And the typical thermal reclamation system are using in natural gas or LPG, and it operates at the different temperatures depend on the binder is used. So this is a very important technology. By using this, we can reduce the use of the sand, and we can also save the environment. The second one is a fume extraction system. Here we can see the old-fashioned fume extraction system some of the foundries using, and that metal melting process generate the gaseous fumes that contain very harmful element of gas. Apart from that, very fine particle of the solid component is also generated during the melting process itself, and that need to be captured by any method or any technological solution available in the market. So nowadays, most of the furnace, if you buy new furnace, as equipped with the removable lid, and that furnace operates in a two mode. First, when the lid is open, most of the melting happen that times, and that furnace operates as the minimum exhaust power, and that lid is removable. So when that lid is open, furnace operates at maximum exhaust power, because at that time most of the fumes need to be captured. Here, right hand side, the picture of the fume extraction system we have installed in our Vadodara foundry. Once the fumes is extracted by the system, it's passed through the filter bag, and after that the filter head is passes through and released via the chimney. Here, the right hand side pictures from top of the chimney, the fresh air after the filtering is passes through. So now onwards, Mr. Darshan Vyas will be explained. Thank you.
So thank you, Deepak. Hello everyone. Myself Darshan Vyas, and I am working at Metso Autotech as a HSC officer, and my education qualification is I am pass out my BSc in chemistry, MSc in environmental science and technology, and post diploma in industrial safety from Gujarat Safety Council. So fumes are very high priority topic. Fume generation is very high priority pollution control for our foundry unit. So as Mr. Deepak announced that we installed fume extraction system with bag filter. Various new technologies are in market. So we installed recently new technology which called reverse air auto cleaning bag filter fume extraction system here. So apart from this, dust is also one of the major factor we have to reduce at our molding area, shakeout area, and also reclamation unit. Also during sand transferring by pneumatic process or old conveyor system, many of lots of dust generated during this process. So dust we can provide dust collector. At Vadodara Foundry, we also installed various areas, dust collectors, small and large dust collectors are provided. Also, these dust collector systems work by drawing the dust and particulate matters like PM10 or PM2.5, and it filters through filter media, bag filters, and separate the particulate matters and discharge purified air back into the environment. So in the dust collector, basic components are blower, dust filters, bag filter, auto cleaning system, and dust removal system. In foundries, dust collectors can be used at many places like I explained earlier, at molding area, reclamation unit, mixer area, shakeout area. Also, we can put at fettling area for grinding dust control, we can put dust collectors. Also, at fume generation at gouging and welding area, we can provide fume extraction system. Portable fume extractors are available in market, so we can reduce fume as well as dust from this technique. Another one area of concern is water pollution. At many chemical industry as well as foundries are generated, we generate lots of water effluent. So we can treat our water effluent at two major part of the treatment plant that called as a effluent treatment plant and sewage treatment plant. So at Foundry, we have zero water pollution policy. So we installed SCP sewage treatment plant to reduce and recycle water of domestic water, which can generate from canteen, water bath area, and also at toilet area. So first water is collected at soak pits, and after that by gravity it will come at STP plant, and we have primary, secondary and tertiary treatment at STP plant. After that we will recycle our water at for development of garden and green belt. Also we can use RO reject water, which is having high TDS in nature. So we are using RO reject water in our quenching media at heat treatment process. Also wastewater from domestic supply can be recycled and used for gardening, and by doing this we can reduce the water usages as well as pollution. Many other new technologies are in market, like energy efficient equipments are available with latest technology, like Foundry need to adopt those technology to reduce energy consumption. Ultimately, it will reduce the impact on environment. For example, there are high efficiency burners are available for complete combustion of LPG as well as PNG gases in heat treatment area. In addition to this, some of the foundries use the refractory coating on heat treatment furnace lining. These coatings has very low thermal conductivity, so it will reflect back heat back to the furnace. It will reduce heat losses. Also, it will reduce LPG gas consumption. Apart from this, Foundry need to adopt new green renewable energy concept. So we can install solar panels as various our Foundry premises where direct sunlight comes. Electricity generated from solar can use in the office area as well as we can use for shop floor lighting. So here right hand side we can see at our parking area on top of the shade we installed recently we installed 60 kW solar panel at parking area. Also we have planned to install 2 megawatt heavy solar system on our production shade. So apart from this, we can use LED lighting instead of normal lighting. That will also reduce our energy consumption, and not directly but indirectly we can contribute to minimize the CO2 emission which will generated at various power plants and electrical sector. Apart from this, we can commonly use one common concept of rainwater harvesting to limit the water uses. So we installed various technologies, but if we cannot measure with pollution factors, so we cannot minimize the pollution source. So we at Metso Autotech, we monitor ambient air quality monitoring, following by the methods of PM10, PM2.5, sulfur dioxide, and oxides of nitrogen. At stack monitoring, we also monitoring particulate matter, sulfur dioxide, and oxides of nitrogen. Also for sewage treatment plant, which we are using at gardening area, so we have to monitor biological oxygen demand, total suspended solid, pH, and residual chlorine to minimize the environmental impact on ground as well as biota. So workplace monitoring also done, in which we are monitoring total dust, sulfur dioxide, and nitrous oxide. Drinking water as well as noise monitoring will done by this standard.
Mr. Darshan, last 2-3 minutes.
Yes, sir. So we can conclude that it is observed that proper use of engineering solution and latest technology, adverse environmental impact of foundry operation can be reduced. Here the most of the solutions are presented, very commonly used in almost new foundries, but foundry should do continuous monitoring and measurement to reduce its impact on environment. Additionally, time to time maintenance and preventive maintenance is required for effectiveness of this equipment and technology. Also, foundry industry need to work more intensively towards waste recycling and adopt new green energy technology like solar panel. Thank you very much.
Thank you. Thank you, Mr. Darshan and Mr. Deepak. You can have the questions. We will have 2 to 3 questions from the audience. So if you are having any queries, you can ask to the speakers. May I request those sitting at the back, please come in the forward front seats so that you can see the slides in a better way. Any question? Mr. Darshan, I have got one query to you. You are from Metso, Vadodara.
Yes, sir.
Okay. Your foundry is a Alpha Set foundry. Am I correct? You have covered many aspects of the pollution and the environmental effects of the foundry operations. One aspect you have not covered. I think in Metso, Vadodara, you are using the solvent-based coatings.
Yes, sir.
So when we are burning these solvents, there is many organic gases getting involved.
Yes, sir.
So how you are taking care for such kind of environmental impact? Can you explain?
Sir, so nowadays many green sand technologies are available in market. So we are taking trial and we will definitely move that technology in future. But continually we are monitoring VOC emissions from sand and coatings. So we are working on that. But after getting positive result, we will explain in better way.
Okay. Thank you. Definitely we need to make our foundry as green as possible.
Yes,
that is the today's requirement.
Yes, sir.
Well, thank you very much.
Thank you, sir.
Yeah. Mr. Suresh, can we have the memento for the speaker?
Good morning, everybody. Topic of my presentation today is the future trends of casting and area of opportunities. Over last 2 days, all of you would have got a lot of insights about castings, manufacturing processes. So I'm going to keep my presentation and the topic succinct and simple. So I would like to thank the organizers for driving the conversation on future trends in casting in this Industry Foundry Congress 2022. Today, I would like to focus on the topic of quality and delivering zero defect in manufacturing of casting industries. A lot of presenters at this forum have already spoken about organizational, cultural, achieving excellence, implementation of continuous and breakthrough improvement, and total quality management, including some of the intelligent systems and the environmental topics. Why quality is important, and delivering of quality, excellence quality, required all of the things what you have gone through, and more, pull together a sustainable plant operating systems that is unable to continually evolve with the ever rising expectation of the customer. Clearly, if we want to make in India for India and export to the world, we need to deliver quality at the level of demanded by the toughest customer. And today I am going to cover some of the topics which can be useful. Along with this, I'm going to cover auto industries in India. I'm not here to answer the question about, Ford's future in India. I'm here only to talk about casting and in general auto industries. And what are the critical to quality expectations from foundries? So, auto industry contribution in past, close to 8% of GDP as per 2019. 19 million people are being deployed. And a lot of recent announcement includes 100% FDIs, and recent announcement about PLI of EV industries are the lucrative futures for auto industry in India. In India, we have got 5 regions, all of you know, and the expectation of this industry will go to 300 billion by 2026. This is very interesting. Auto industry has seen up and down since it started. But 2016 and 2017, we had a golden era where you see upscales. And if you look at the linear scales, the industry is progressing in a positive direction. Research from Counterpoint suggests we had a CAGR low, but if you look at third best year in 2021, after 16 and 19 was 21, over 3 million units of passenger vehicles were sold. So again, a great future ahead. This is from CRISIL. The way you read this chart is, this was a survey done by what is the customer expectation and what do they think about demand to bounce back, and this was done back at around a year back. So construction and the real estate, the circle indicates 40%, the red dark indicates above 40% responses says that is 46%, that demand will bounce back. 21% to 40% responses says Q4 2021 it will bounce back, and 33% said it will bounce back in 2022. Look at carefully the auto components, commercial vehicles, 50% demand will bounce back in 2022, and passenger vehicles, financial year 2021, 48%. And we saw that 30 million vehicles sold, right? So it's, and remaining 30% will grow. Two-wheeler industry had a great turnaround in 2021. Coming back closer to the casting industry and specifically to aluminum, electric vehicle cells, now this is about EV, not ICE. EV demand is going to exceed 40 million by 2030. And if you look at aluminum demand for EV specifically, 2025 to 2023 upswing, which is quite significant. And this is already happening. If you look at other part of the world, Europe, North America, China, technologies are improving. The old foundry technologies are going out and the new foundry technologies are coming up. So this is what is happening in other part of the world, as well as OEM investing heavily on the electrical vehicles. What's the future? Casting industry for automobile, when one speak, it's about 4 components historically: head, block, crank, and gear case housing. But from present to future, if you look at electrical vehicles has got significant increase of the aluminum die casting, high precision aluminum die casting. It includes e-motor housing, battery housing for plug-in hybrid and battery electrical vehicles, and fuel cell housings. Interestingly, lot of body component, where we see a sheet metal now, are also getting changed to complete aluminum die casting. So if body in white, the shock absorber, mountings, the rear rails, A-pillars, from the driver's seat is left and right A-pillar, B-pillar and C-pillar, the full subframes and the cradles where batteries and the trans casing is mounted are also getting developed towards lightweight casting. And this is a significant step change from where the casting industry is to get ready for the future. Because a lot of talks about if internal combustion engines gets out, what's the future of casting? But this is a future. Some of the examples of high precision aluminum die castings. So the right-hand side picture is about the front cross member, where actually the powertrain component sits, and the shock absorber tower, and the rails. These are all built with aluminum die casting. So you don't have to manage complexity, don't have to manage welding parameter, etc., etc. And it is a lightweight, which improves the emission as well as the strength to weight ratio, fuel efficiencies. To deliver this, what are the critical to quality parameter? So if you look at input, in foundry industry, temperature, velocity, pressure, and solidification, these are the critical input parameters. When we talk about SIPOC, right, it's all about how you measure your input so that your output is predicted, good or bad. And when bad is prediction, we do correct so that the customer don't get bad quality. If it is not managed well, impact to product quality defects, all around hot tears, cold certs, these are all foundry terms, so I'm not getting into detail. And it costs a lot to the foundry as well as the OEM. Control measures, what we can put in place is the feeding systems, thermal balancing, real-time process monitoring, AI technologies, and automatic detection of the process parameters. So if anything goes wrong outside the control limit, the process stops producing bad quality part. What can be done in a pre-advanced stages is about simulation, flow, magnaflux, some of the die enhancement plant, surface treatment, AI cameras, vibration monitoring, heat temperature monitoring, etc. When things goes wrong, it's a major cost to the company, including OEM as well as the foundry. and it calls recalls, bad brand images, etc., etc. So if we have to get out of this, I think the way is to focus on input and have a very solid quality process control. Getting further detail, the expectations from the foundries. So it categorized in 4 different categories: material, sand management, tooling, and simulations. And further down, there are various methods available for material, raw material check about radioactivity. If we have a separate grades, identification of the grade by material, so you can prevent the mix. Specs for raw material, very control, and in-house spectrography, so that you can do very quick check, audit of the raw material. Sand management labs following the American Foundry Society standards for grain finishes and checks, and sand reclamation and recycling, including environmental friendly processes. Tooling, in-house local tooling, geometry check, time to time, always have a backup of the dies, and very solid die prove out and product launch process, and follow the complexity casting check process. And simulations, actually many foundries does the simulation as a part of product launch because that's a customer requirement. But then when things goes wrong, going back to simulation and understanding whether that was done right or wrong and what improvement needs to be done is a key area of gap. And that only comes when there is a problem. So key area of opportunity is there. When we talk about quality, very close to personally me, this is what it is, right? When nobody is saying doing the right thing is about quality. Very interesting chart here. And this actually signifies the cost of poor quality. So far left is the customer. And then start with the tier 3 sub-supplier. What you see, the red walls are the quality wall and checks. As we get closer to the customer, the wall get reduced. So our opportunity to detect the defect get actually reduced. And below, the cost of poor quality multiplies, sometimes 1,000 times. So if there is a porosity in the casting and there is an engine change, right? The complete engine change gets to the foundry. Now, if you have complete process parameters, temperature, process, all those parameters checked and controlled, you can detect this, right? So that you can stop producing bad quality parts. So cost of poor quality significantly increase as the bad defect goes to the customer. And finally, measurement of the quality. Everybody likes higher numbers of the FTT. And this slide is very interesting. If you look at the top side, if you have a processes in casting, you have a step A, step B, step C, steps D. And if you have a very good check about what you are putting in, what you are getting it out, and then do the roll throughput, that's a real measure of roll throughput. Rather, putting 100 parts, get 90 parts out okay, you say 90% FTT, but that's not the case. For the similar process, if you apply roll throughput, it will be 79% because you are spending energy, labor, everything to process it. And whatever is in process rejection is cost and the waste. So this is where you may want to think about how you want to rejig the measurement of quality in your processes. So with that, I would like to conclude and thanks IFC 2020 team for giving me this opportunity to share my thoughts about future trends in industries and expectations from foundries. Thanks very much. Namaste.
Hello. Thank you, Mr. Patel. Anyone having any questions, queries to the speaker? Yeah, please. Can we have the mic for the person?
Hi, good morning. I'm Tanay Anjikar. I would like to ask a question that our speaker, Mr. Anil Patel, he majorly spoke about die casting. I just wanted to ask what would be the scope of investment castings in automotive moving forward?
I think, yeah, so I think investment casting, precise small components also has got a feature. But if you look at the die casting has got a major feature in the industries as we go towards the EVs. Die castings are very, very limited right now. Small clamps, etc., high precision in investment casting. But the major feature is on the die casting, the major components. But, but clamps on the batteries, for example, high precise can be opportunity for investment casting.
Thank you.
Anyone else? Yeah, please.
Good morning, sir. My name is Imtiaz Ali. I just want to ask you one thing. In your views, Industry 4.0, artificial intelligence, IoT, how does this thing can help to improve the quality?
Yeah, very good question. Thank you, Imtiaz. I think uh, Industry 4.0 and big data analytics, in my view, it can tremendously help the industry if there is a thinking behind what actually we want to achieve. And the reason I say this, nowadays there is a big push about data collection, data gathering, and there is a tons of data, thousands of dashboard. But actually we need a humanware to interpret those data and make the right decisions. So any Industry 4.0 application, I would ask what ultimate benefit it is going to give me in my operation. Is it going to improve my quality, reduce waste, improve the cost, and do I have a sufficient members who can interpret and analyze the data and make the real-time decision, right? Because manufacturing industry follows the tech time. One day delay, opportunity loss. So yes, it has got a lot of benefit using various cameras, the thermal monitoring, the predictive technology, connecting machines. A lot of data can be made available, but setting the right baseline, right? And identifying the outlier and working on that is a real effective use of Industry 4.0.
Thank you. Very well explained. I hope your query is sorted out. Anyone else? We can have the last question. If anyone is having. Well, thank you, Mr. Patel, for your presentation. Can we have the memento? Mementos, please, ma'am. Well, the next speaker is Mr. Adithya K. He is a senior engineer, metallurgy from R&D department, PK Steel Castings, Coimbatore. His topic for today is amalgamation of metallurgical theories and foundry traditions of ASTM A995 slash 8995M Super Duplex stainless steels. He is a postgraduate in metallurgical engineering He's a ISO 9001-2015 lead auditor and ISO 17025-2017 internal auditor. Has published many papers and written monographs on metallurgical topics. He is an international technical member of AFS. Over to you, Mr. Adithya. You can have your presentation. Thank you.
So good morning. Thank you, sir, for your introduction. So today I am planning to discuss about the amalgamation of metallurgical theories and foundry tradition. So why this topic of amalgamation? Because basically the metallurgist, including me, we speak lot of theories. But when it is coming to the applicability in the foundry, we have lot of doubts how to interpret the theory and the practical things. For example, we will have a cardiologist, he may have 100 patients. So 100 patients' health condition will be different. 100 different situations. So that particular doctor has to analyze each and every patient and should study their own patient and have to give the solution for them. So similarly, a metallurgist in each foundry, we have 100 number of foundries and 100 foundries have 100 different parameters. So we have to understand first our own foundry and we have to mingle our metallurgical theories with that particular foundry's practical situation. And why this ASTM A995 super duplex stainless steel is because now the entire industry is turning from super austenitic stainless to super duplex stainless steels because of their enhanced corrosion resistance along with the mechanical properties. So today we will see just about duplex stainless steels and what is the metallurgy of duplex stainless steel and the characterization of duplex stainless steel using various methods like metallography and XRD analysis and SEM and EDS analysis and interpreting various phases that are forming, and we will see some conclusions out of that. So basically duplex stainless steel is a family of stainless steel. It is a bridge between austenitic stainless steel and ferritic stainless steel. So this material basically contains 30 to 60% of ferrite phase and remaining austenite. And it has an excellent corrosion resistance for stress corrosion cracking due to presence of ferrite. However, the same ferrite makes the material susceptible for hydrogen-induced cracking. So this material is particularly restricted beyond the application of 350 degrees Celsius because of formation of various secondary phases that we will see in the upcoming slides. So here we can see a graph which is showing different kinds of stainless steels that we produce, where the if you see at the top, we will have austenitic stainless steels, which is mentioned as A, and at the below right column, we will have F, which are ferritic stainless steel. And we can see the ferrite content A plus F at the right corner, which indicates the percentage of austenite and ferrite wherever duplex stainless steel belongs to. So the solidification of duplex stainless steel is a typical solidification which is entirely different from all the other steel materials, including carbon steel or stainless steel, even austenitic stainless steel and ferritic stainless steel, because in this the solidification starts with ferrite phase followed by austenite transformation below 1000 degrees Celsius. And the advantage of duplex stainless steel is that we have addition of nitrogen. So this addition of nitrogen actually promotes the nucleation and growth of austenite phase in the material at high temperature. And during solidification, there are various phases that forms, unlike austenitic and ferritic stainless steels, like nitrides, carbides, and lot of intermetallics. So this is the solidification pattern of a normal stainless steel based on the chromium and nickel equivalent, as we know. So discussing the solidification of duplex stainless steel, which is drawn by the blue line, we can see the solidification starts from liquid. So once the material reaches around 1500 degrees Celsius, the solidification starts, the liquid transform to liquid plus alpha. So below 1450 degrees Celsius, we will have 100% alpha, and on further solidification and further cooling process, the new phase, that is austenite, starts to form. And this continues up to 800 degrees Celsius, and at 800 degrees Celsius, the third phase starts to form, which is the sigma phase. So the 850 is the degree Celsius where it starts with sigma and continues the formation of various phases like psi phase, nitrites, carbides, G phase, R phase, n number of phases starts to form. So you can see this is a typical TTT diagram of a duplex stainless steel, where we see n number of phases, not like the other steel that is chromium carbide, sigma phase, chi phase, nitrates, secondary austenite phase, R phase, pi phase, epsilon phase, alpha prime and G phase forms. And we can see the effect of each alloying elements. Particularly if we see the alloying elements that increases the tendency of these secondary phase formation are all ferrite stabilizers. For example, chromium, moly, tungsten, silicon. So these elements are the elements that stabilizes ferrite and reduces the percentage of austenite. So whenever I am increasing my chemistry with these particular elements, automatically the ferrite phase increases, that induces the formation of so many secondary phases as we see here. So main issues that a foundry faces with the super duplex stainless steel are these four, which is gas, inclusions, crack and shrinkage. So these are the some of the root causes that we have identified with particular to duplex stainless steel. But the major problem with duplex stainless steel is cracking. So root cause of sigma phase, generally we all know the root cause of cracking is sigma phase. So whether is really a sigma a problem? Yes, sigma is really a problem. But is really, we have to think, is really sigma is the only problem beyond the crack tendency? It is not. So is there any other sources that form cracking in super duplex stainless steel? Yes, we have number of reasons. Are these reasons that lay behind the formation of sigma phase? Definitely yes. So what is the real fact behind the sigma and its byproduct crack? It is chemistry designing. So basically we have to start from the chemistry designing for duplex stainless steel to control cracking. So basically we all know this duplex stainless steel is susceptible for sigma cracking, but it is not the fact. Sigma phase is one of the phase that forms at high temperature, but we have also another phase that is forming at 475 degrees Celsius, which is called alpha prime phase, which during steel foundry we used to weld the material to do some repair work, or during the gouging operations we expose the material to some heat. Whenever the material is exposed to 400 degrees Celsius and above, there is a chance for formation of alpha prime phase. So that will create 475 embrittlement in the material, and at high temperature we will have sigma phase cracking. So to understand this behavior, we actually made some ASTM A995 4-leg keel blocks. So this is the drawing as per standard. So these are the melting parameters which we maintained during the test block pouring. So these are the test block which were poured with the above parameters. So material details. The chemistry we maintained in the steel is shown as, and the Pren we got is 41.52. And the microstructure of the material after solution annealing shows clean austenite and ferrite phase free of secondary phases, and the ferritoscope shows 44% ferrite, and through image analysis we get 45% of ferrite. And the impact test done at minus 20 degrees Celsius showed 164 joules, average of 3 samples, and this material we took for trial is grade 5A. So further, this solution annealed material is subjected to XRD analysis to understand the basic characteristic of the material, and we can see austenite is around 57.5%, ferrite is around 42.5%. The crystal structure of the material is clearly displayed that austenite has face-centered cubic system and ferrite has body-centered cubic system. So this is the crystal structure simulated from the actual data taken from the material, showing the ferrite with BCC structure and austenite with FCC structure. So now let us try to understand what is 475 embrittlement and what is sigma phase embrittlement. So to understand the 475 embrittlement, let us see the iron chromium phase diagram, where we can see below 450 degrees Celsius, that is around 500 degrees Celsius, we are having a red line below which the phase present is alpha plus alpha dash. But when we do the direct quenching from the higher temperature of 1080, we will not have this alpha prime phase because we are directly quenching from the high temperature where we will have only alpha plus gamma. So when my material is further heated above 350 degrees Celsius, what happens? This metastable alpha prime phase, alpha phase starts to transforming into its stable phase of alpha and alpha dash. So to understand, first we took one of the test block and we heat treated at 475 degrees Celsius for 24 hours and some metallurgical characterizations are done. But in metallurgical characterization, you can see in metallography, we find no difference in the microstructure. There is no differentiation of alpha and alpha prime because it is difficult to segregate the material at microscope level. So further characterization is required, but ferritoscope, however, shows 43% of ferrite. We have two phase, but it is showing still 43% of ferrite. Why? Because both alpha and alpha prime are magnetic phase. So we cannot segregate through ferritoscope also. However, if we see the impact toughness of the material in solution annealed condition, the impact toughness is around 164 joules. But after exposing to 475 degrees Celsius, we can see a great fall in the impact toughness to 16 joules, which is nearly 10 times the impact toughness of the material is dropping down, indicating the material has become brittle. Now further we took some other test blocks and we heat treated at various temperatures like 400, 475 and 500 degrees Celsius, and we tested for hardness and impact toughness, where we can see the hardness of the material at 475 degrees Celsius drastically increases, indicating the material forms this alpha prime phase at 475 degrees Celsius with highest kinetics. However, the impact toughness also, if we see, the impact toughness of the material falls suddenly to 26 joules from 160 joules. Whereas at 400 degrees Celsius, we can see a linear drop in the impact toughness. But if we see in this, at 500 degrees Celsius, only the hardness of the material increases, but the toughness is not dropping down. So what does it mean? Whether the material is not brittle? Yes, the material is not brittle beyond 500 degrees Celsius to 600 degrees Celsius. Because 500 degree to 600 degrees Celsius, we have no secondary phases forming in duplex stainless steel. So to validate that further, the fractography of the images are shown, which is clearly showing brittle fracture. So to nullify the effect of 475 embrittlement between the 500 and 600 degrees Celsius, we carried out redissolution treatment at 550 degrees Celsius. So you can see there is a gradual recovery in the impact toughness of the material from 22 joules to 158 joules. So this is the concept of 475 embrittlement and redissolution treatment. That is one of the solution to overcome the 475 embrittlement. And the second main crack we all discuss, entire foundry industry speaks about, is the sigma phase cracking. So we can see this is the phase fraction that forms in a duplex stainless steel between different temperatures.
Mr. Adithya,
yes.
last 2-3 minutes.
Yes. So this blue line indicates the ferrite phase and red line indicates the austenite phase, where you can see between 600 to 1000 degrees Celsius, we have no ferrite, indicating the formation of sigma is high between this temperature. So further to understand, we did some other trials with at 750 degrees Celsius and 850 degrees Celsius, indicating there is a fall in impact toughness with increase in hardness. And the ferrite phase gradually decreases because the sigma phase forming in the material is a non-magnetic phase, so we can easily identify the sigma phase using ferritoscope. So you can see at 750 degrees Celsius, the secondary phase formed is very finer than the secondary phases formed at 850 degrees Celsius. And the fractography image shows clear brittle fracture. So further we did some XRD analysis and we understood at 750 degrees Celsius, the secondary phase that forms is actually not sigma phase, it is actually chi phase, which is BCC crystal structure. Whereas at 850 degrees Celsius, the secondary phase formed is tetragonal structure, which is sigma phase. So it is very important for us to understand that two phases are forming in duplex stainless steel, which is chi phase and sigma phase, which increases the brittleness of the material and reduces the toughness and produces crack. So we can see this is the ferrite and austenite which we earlier saw. And you can see iron chrome moly intermetallic, which is BCC crystal structure, which is chi phase, and some iron nitrates are forming between 700 degrees Celsius. And at 850 degrees Celsius, the secondary phase formed is tetragonal crystal structure, which is sigma phase. So we can see there are sublattices of, these are the sublattice points of sigma phase. Now from customers, we are getting a lot of stringent requirement with higher print. Possible difficulty we face is higher print, high alloying elements like chrome moly and tungsten. So chrome moly tungsten, what it does, it increases the cracking susceptibility of the material. But really, is print a problem? Yes, and sometimes no. So we have to understand when print is a problem. So print is a problem because of the alloying elements that we add to meet the print number. So why alloying elements? Because the elements we add is chrome moly and tungsten, which increases the ferrite phase, which subsequently increases the sigma phase, which is hard and brittle. So when cracking happens, it happens at solidification, casting, handling, and heat treatment, and it happens at corners, section thickness variation zones, thin wall section zones, under rises. So when the print is not really a problem, when we restrict the addition of ferrite stabilizer, creating limited to control the ferrite. So controlling the ferrite controls the sigma. Drastically, the brittleness of the material also we can reduce. So methods to achieve print, first we think about addition of chrome and moly because it is easy to add. Yes, it is good idea, print is achieved, but the susceptibility of the cracking increases. So what we have to do? Should I increase the nickel to increase the austenite phase? Yes, it is a good idea, but the production cost with the current scenario is not possible, and it is where we have to control. So what are all the, so to understand the better, we did some prototyping of a simple disc in our foundry. So you can see the left side is a grade 5A disc made with print number 42.33, and the material is having crack under riser where the ferrite is around 54 to 57%. One at the right you can see is the disc which is made of 5A with print number 43.72, but the ferrite what we achieved is 42 to 44. So it is better, it is up to us to control the ferrite by monitoring the chemistry of the material. So these are the elements which you can see can help in increasing the ferrite, increasing the austenite, nickel, nitrogen, carbon, and manganese, and they also have their constraints in addition. So other parameter what I can do is to control my heat treatment parameters by optimizing the temperature, time, cooling media, and heating parameters. So process and results varies for foundries depending on their production process and methodology. So it is very important for us to understand our process, our methodology, and how we process the material, and to find the solution out of this. And one more thing what I feel to tell everyone is, if we treat the material as a living being, it will definitely react to us back. So with this, I hope this will be a useful presentation, and I also thank IFC for providing this opportunity to share some of the tips that we can share with the entire foundry industry. And I also thank our management, Mr. Taufik Moidu, who is not able to come because of some health issues. So I thank him for providing this opportunity, and our chief operating officers, Mr. Sabi and Mr. Rajesh, for motivating me, and Mr. Muthu, our quality person, who has supported a lot in this project, and Mr. B. Raha, our GM Metallurgy, for their entire support during this project. Thank you.
Thank you, Mr. Adithya. Can we have questions? Yeah.
Hello, my name is Ankit Doshi.
Hello, sir.
We are a manufacturer of stainless, we are a stainless steel foundry. So we have observed that in Super Duplex 5 and in 4A, sometimes without any reason, all the parameters are okay. A lot of gas occurs, lot of blowholes kinds. And in the same heat, bigger casting is okay, and it comes in the smaller casting. So is there any technical phenomenon or any reason for this?
Yes, sir. Coming to this gas porosity with varying section thickness, the main parameter which we have to control is from the pouring. So pouring is the main area, melting and pouring is the main area where we can control these gas holes, because we may have to select the pouring temperature based on the design, based on the wall thickness of the material, based on my molding system, and also we have to monitor our mold, because if our mold coating is not completely cured, or if I am just directly pouring without any curing time, if my coating is still wet, so that will also become a part for gas porosity. And sometimes core gas release is also a problem when it is coming to the mold section. So every parameters that we have to check for controlling the gases in molding and melting area.
Yeah. That gentleman, yeah, please.
Hello.
Hello, sir.
Yeah. First of all, this was a very nice and informative presentation. So thank you very much for that.
Thank you, sir.
I am Tushar from Siemens Energy. I have a very general question. If there is a alloy steel, say AISI 4140 or 4142, and it is suitable from minus 20 degrees Celsius, and if a sample piece is tested at room temperature and property derived, then is it any correlation or some method so we can
Sir,
show
sorry, I can't hear, sir.
Please
Hello.
speak loudly.
Hello.
Yeah.
Is it okay?
Yes, sir.
Okay. It is a general question. If there is an alloy steel, AISI 4140 or 4142,
Okay, sir.
if we test it at a room temperature and some properties we noted down, is it any correlation or any method that we can show that this material is suitable at minus 20 degrees Celsius and the property will be like this based on the room temperature testing? Is it there?
No, sir, it is not possible. Actually, that is why even in our EN requirements and also PED and NARSAC requirements, they ask to test at the lowest operating temperature so that our material will be suitable for any higher temperature beyond that. We cannot guarantee a material by testing at minus 20 and I cannot guarantee the same material for minus 30. So it is not possible, sir. We have to test at the lowest possible temperature to meet the requirements so that I can apply my material beyond that temperature, particular to impact toughness.
So particularly for minus 20 degrees Celsius, we have to derive the test result.
Definitely, sir.
Okay, that is. Thank you very much.
Thank you, sir.
Anyone else?
Good morning, sir.
Good morning, sir.
I am from Indian Railway.
Yes, sir.
We are manufacturer of rail wheels for coaching and boxing.
Okay, sir.
We have pressure casting. Sometimes we are getting slag in middle order. What is its problem and how I can avoid it?
Sir, that's what I told. To understand such process defects, we have to study our entire process because the process varies from foundry to foundry. So that to understand why the slag is forming, we have to start studying from our melting process. So whether we are doing correct deslagging process, whether the slag in the ladle is coming into my material, whether any slag is forming inside my mold, because when I expose my material to the atmosphere, automatically
we are using graphite mold. It is a permanent mold.
Okay, sir. But I don't have idea on that actually.
Thank you, Mr. Aditya.
Thank you, sir.
Thank you very much. Okay. This will be the last question, or otherwise afterwards you can have a one-to-one interaction with the speaker.
Yeah, I was a bit surprised to see that in your presentation you mentioned that the cracking is because of root cause for cracking is the metallurgy. But there are literatures for super duplex that heat treatment plays very important role in order to control the cracks. So your views on heat treatment, because this could be one of the possible reason.
Yeah.
Apart from metallurgy, this is the one thing. And second thing, the maximum temperature of these alloys are 350 application temperature. and you have done a lot of working on 475 embrittlement. How does it going to help the actual users, this 475 embrittlement work?
Yeah, see, 475 embrittlement I speak about because many of the people deal with thin wall castings. So when we are doing some repair work or removing the riser and gating system in thin wall casting, we subject the material to high temperature. Whatever the cooling method we use, even if we do some water pouring and do the cutting, there will be a localized higher temperature which is experienced by the material. So when the material is subjected to because anyhow the material is not going to be on 850 degrees Celsius, however it can go up to 500 degrees Celsius. So it means that from the cutting point, there is a point where 500 degrees Celsius is exposed. So it means that from 1000, 900, 800, 700, 600, 500, 400. So there is a temperature where the material is also exposed to 475 degrees Celsius. But we always say only because of cutting, high temperature exposed, sigma phase formed, cracking came. So this is what the overall picture we see. But there is also a temperature which is creating a problem, which is 475 embrittlement. So that is very important to understand during welding of the material, during riser and gating system removal time. So that is why I try to explain the same. And also I mentioned that chemistry is one of the solution to control the sigma phase. The other solution is to play with the heat treatment. So if we are not able to control the chemistry, then the only option I have in a metallurgist hand, whoever the metallurgist, he has two options in his hand. He deals with chemistry and he deals with heat treatment. So once he is not able to control with chemistry, then his second option will be with heat treatment.
Thank you. Thank you, Mr. Adithya.
Thank you, sir.
Can we have the memento for the speaker? Well, friends, the next speaker was in fact Mr. V.N. Satyanarayana from Disa, India. But Mr. Per Larsen has come all the way from Denmark to present this particular paper. His designation is Innovation Manager, the company Disa, Denmark. His educational qualifications are, he holds Master of Science in Foundry Technology and PhD in thin wall ductile iron castings, and he has got experience of almost 26 plus years of Disa line. His topic is making aluminum castings in green sand, exploring the benefits and challenges. Mr. Per Larsen, the floor is yours.
Thank you very much for the introduction. Let me try to start this. So, thank you very much. The topic for today, that is non-ferrous castings produced in green sand. And today we will talk about aluminum castings and brass and bronze castings produced in green sand. We have produced a small agenda for today. First, we will start with a short introduction. Then we will say a few things about molding and sand plant. And then we will talk a little bit about pouring. And then we will show quite a lot of examples of aluminum castings successfully today being produced in green sand. Furthermore, we have prepared a number of examples for brass and bronze castings, also today successfully produced in green sand. And then finally, we will conclude. So, let's jump to the introduction. I think everybody accepts that green sand molding, and especially virtually green sand molding, is a very, very efficient way to produce iron castings. Both producing aluminum castings and brass castings in green sand can also benefit from this very high cost efficiency. that iron castings benefit from today. Many non-ferrous castings are already being produced in green sand today. For instance, if we look towards the US, we will see a lot of foundries both producing aluminum in green sand with success and brass and bronze in green sand with success. Unfortunately, this is not so widespread yet, so today we would like to give some details on how this can be done. So, in general, these non-ferrous castings, meaning aluminum castings and brass and bronze castings, are normally not made in very high volumes. Hence, we will try to focus today on solutions that are more suitable for producing castings in smaller volumes. If we look at producing non-ferrous castings in sand molds, there are a lot of benefits. Of course, they depend on which process the castings were produced in before. So the list I will show you today on benefits can be seen more as general benefits and covering most of the different processes. But of course it will be specific due to the specific process that we have converted into a green sand casting. So first of all, when we talk about green sand molding, we have this very high efficiency that is hardly found in any other process. Then we have a very simple and efficient core setting that will mean we can produce castings still at a high rate, even though they are cored. Then we have the chance to change tooling, meaning pattern plates, very fast. When we in the green sand process want to produce another part, we only need 1 or 2 minutes, then we are ready to produce the next casting. Depending on the need for service life of the pattern, we can choose many different materials. So we can use everything from hardwood to tool steel patterns, depending on what tool life is needed. And this means, of course, also that the costs for tooling can be kept very low and in proportion to what is needed. If we only have to run short series, we can produce the patterns in hardwood. If we need to run extremely long series, we can produce the patterns in tool steel. So these pattern plate lives can be very high, and as high as 500,000 or even more if we go for tool steel. This means at even very high production volumes, we only need one set of production patterns. We don't need a number of toolings to be able to make the production. Furthermore, the pattern maintenance will be very low when we compare to other processes from which these castings normally are moved. We do not have to repair weld on a die every 5,000-10,000 shots or something like that. We can use the patterns for hundreds and hundreds of thousands of molds if we produce them in the right material. Furthermore, as the tooling normally is quite simple, the lead time from a 3D CAD model to the first prototype can be very short, and of course also the lead time to the start of production can be very short too. If we need to do modifications, optimize the gating systems or feeders, it's also very easily done on a pattern for green sand molding. So some of these points will be discussed in this presentation. Unfortunately, the time is a little short, so we will only highlight some of the features. So moving on to molding and sand plant. If we are going to produce aluminum or brass and bronze castings in green sand, the molding machine will be exactly the same. This means we have a proven and very efficient technology available. If we look at aluminium, then we will see that the tendency of penetration will be more or less the same as for iron. And this is because the wetting is much stronger for aluminum, but on the other hand, the density of aluminum is much less. So at the end of the day, we will have more or less the same tendency to penetration of aluminum as we have for iron. And this means that we can get very good surface qualities of castings coming from green sand molds, even though we use sand as molding material. If we look at brass and bronze, we will see that the tendency to get penetration is quite a lot bigger than for iron. To mitigate that, we normally recommend molds with lower heights, let's say 400 to 480 millimeter, to have a lower risk of getting penetration on the castings. If we look at the molding sand we use for aluminum and brass and bronze, we use quartz in both cases, and as with iron, we use bentonite and water to bound the mold. Properties for the molding sand will be similar to the molding sands used for iron. Typically, we are not using coal dust when we produce aluminum and brass and bronze. Properties of the molding sand will of course have to be adjusted a little bit to the actual application, meaning are we pouring aluminum or are we pouring brass? In case we are pouring aluminum, we will try to keep moisture a little bit on the low side to reduce the risk to get hydrogen pickup. Are we talking about brass and bronze? We will try to keep the grain size at a lower level to reduce the risk of penetration. Core setting will be done in the same way as you know from iron foundries, meaning we have a proven and very, very efficient process. So running core castings is actually one of the places where moving to green sand will give you the best benefits. If we talk about aluminum castings and brass and bronze castings, we typically talk about shorter volumes. This means it can also make sense to do core setting by hand. Doing core setting by hand, we can also set very, very complex cores. We can use nails for fixing the cores in the molds, etc. We can also set non-glued core packages if we would like to do that. We can even use two operators, one from each side of the machine, to speed up the setting of the cores into the mold. So with this setup, and even though we use manual core setting, we can easily run 100 molds per hour without too big problems. We can of course also run the molds horizontal and use a match plate machine to produce the molds. And again here, as we saw for the vertical molding, we will use proven technology being used for iron for many, many years. If we look at the sand plants, typically you will see a sand plant as quite a big installation and also quite a costly installation. But are we talking about these smaller production volumes? We don't need to go for these big and costly installations. For say 100 molds per hour setup, we can use a much, much simpler installation and hence also a much, much cheaper installation. And here we see an example of a simple sand plant suitable for around 100 molds per hour. This of course also means that it will take up less floor space, and what is even more important, that total investment will be much smaller both for the sand plant and also for the molding machine. So actually it will match this smaller production capacity. Molding, especially when we talk about vertical green sand molding, people normally think 300 molds per hour, 400 molds per hour, even 500 molds per hour. But when we talk about modern green sand molding, we now have available solutions that both fit these huge volumes normally produced in green sand and also smaller volumes which are relevant for non-iron castings. Here we see a list of some of the available molding machines. We have the D3, which is one of our high runners with up to 555 molds per hour. And then we have a new group of molding lines with the C line, a vertical molding line, with speeds from 150 molds per hour and up. There's also new and smaller match plate machines available, which suits very well the smaller production volumes normally seen at these non-ferrous castings, meaning both aluminum castings and brass and bronze castings. So we can say that now we have modern and affordable molding equipment available that also suits these smaller production volumes. And of course also the investment will follow this. Okay, let's move on to pouring. For most aluminum castings and brass and bronze castings, hand pouring is a good choice. It's a simple way to pour the mold and very flexible way to pour the mold, and most of these castings can easily be poured this way, and it matches very well the smaller production volumes normally seen for these castings. Are we talking about aluminum? Sometimes it's a little different. Aluminum forms oxides very fast, and these oxides, they will reduce the mechanical properties. And in case we are producing aluminum castings where we need to obtain the highest possible mechanical properties, it is super important to reduce the formation of oxides to an absolute minimum. This means we need to have a laminar flow, and we need to avoid splashes of the metal, etc. We obtain this by using low pressure pouring, where we fill the metal through the side of the mold and slowly fill the metal into the mold. To get high productivity, we have a small core closing the runner bar, meaning we can move away from the mold with the pouring device before the metal is solidified. And how does that look in real life? Here we see the mold. We see the nozzle on the pouring device docking to the side of the mold, and we see these small cores we use to block the runner bar when the mold filling is over. This is how it looks in real life. We do mold transport, we dock to the side of the mold, then gently we fill the metal into the mold, and when the mold is completely filled, we close the runner bar with this small pneumatic cylinder pushing the core into the runner bar. We can move away, do mold transport, and then pour the next mold. So even though we have this system, we can still reach quite high production speeds. This will of course mean that we have no manual interactions in the in the pouring. So we are not relying any longer on skilled persons pouring the molds, and we can also save personnel in the foundry. Here we see a picture of a pattern where we see a very simple gating system needed for this system of bottom pouring. So this was a little bit about the technology that we use to produce aluminum and brass and bronze castings. Now let's try to look at some examples of castings produced with success today in green sand. First of all, we have to say when we talk about aluminum castings and green sand molding.
Mr. last 3 minutes.
3 minutes, perfect. When we talk about green sand molding, then most of the castings are moved from gravity die or low pressure die. We can say many of these castings can be moved to green sand molding. And if you have any doubt about castings possible being moved to green sand, then please don't hesitate, contact us. We have the DISA team of application engineers that will analyze the parts, and then we can find out together if we can convert these to the green sand process. So let's look at some examples. Here we have a cord casting, a tank inlet produced in Denmark, a bearing sheet produced in Germany, ventilator wheel also produced in Germany in green sand, pneumatic control valve. So now we move into a little more demanding castings. This casting will demand pressure tightness. Another casting that will demand pressure tightness. We can also do aesthetic castings. If we take a little bit more care about the sand parameters, we can reach super good casting surfaces. So even aesthetic castings can also be produced in green sand. Here we have an example of a hydraulic block where we have requirements to pressure tightness, and we also have requirements to the mechanical properties. A connector for a fire hose, a critical part. Of course, this part cannot break in operation when it's part of a firefighting system. Gas valve also a casting produced successfully in green sand, and also a casting where we need pressure tightness, compressor housing. Then some bigger castings, clearly also bigger aluminum castings are being produced successfully in green sand. Here we have an example of a 10 kilo casting, another example of quite a big casting. More complex castings can of course also be produced in green sand, like this heat exchanger. Then a manifold. Of course we know that e-vehicles are taking over, but still a lot of ICE vehicles are being produced. So for instance, here we have a manifold being produced in 7 million pieces in France with great success. Transmission housings can also be produced in green sand with great success. Last but not least, also more demanding castings with higher requirements to the mechanical properties can also be produced in green sand if that is needed. So that was aluminum. Let's try to look at some examples of brass and bronze castings also being produced successfully in green sand. And I guess one of the most typical castings will be fittings. A lot of fittings are produced around the world in green sand on diesematic lines, like this one, which is produced in the US. Different covers are also produced successfully in green sand all over the world. A valve body actually produced in my home country on a small diesematic. Another valve, a little bit more complex, but as we talked about earlier, setting cores in the green sand process is normally quite easy, so making these castings with more complex cores is not very difficult. A last example, impeller, and then a further example of aesthetic casting also. This is the body for a lamp, where we need a super good surface quality, and that can also be obtained in green sand if we again pay a little extra attention to the sand properties. So let's try to move to the conclusion. So what we know is that green sand molding, and especially vertical green sand molding, has proven to be a very cost-efficient way to produce iron castings. I think nobody will argue that. But we can also see that this cost efficiency can be transferred to both production of aluminum castings and brass and bronze castings. And we have shown that with, I think, quite a number of casting examples shown today from different places around the world. So I think we can say that both aluminum and brass and bronze castings can be feasible produced in green sand molding, and that we now have modern molding equipment available that matches these often smaller yearly quantities which these castings are produced in. So I think with these words, that was the end of my presentation.
Thank you. Thank you, Mr. Patel. Since we are running short of time, I would like, if anyone is having any query, you can talk to the speaker, because the next technical session is to start by 12 o'clock. Can we have the mementos, please? Thank you very much for your patient listening to the speakers. We will have the next technical session now.
Hello. Yeah. I would request Mr. Suresh Chavan to felicitate Mr. Sushil Sharma for conducting this session.